Hey, 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 hello, students. Today, we're going to pick up where we left off yesterday. Yesterday, we were talking about speed and velocity. We're going to be adding more information to that topic today. So let's make sure your books are ready and you are prepared to jot some notes down as we continue with our topic on motion. And we begin today with the word, whoops, that's not a word. Word. Bird is the word. The word is acceleration. 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 It is a word that you are probably familiar with, but we are going to be elaborating on it quite a bit today. Now, I am sitting in a chair right now that is on wheels, and I can wheel back and forth. Now, imagine if you were sitting on this chair with wheels and I were to push you around the room, or around the whole building. How much fun would that be? In fact, that's what I normally would be doing with you. But imagine you're sitting on the chair and you're stationary at first. I come up behind you and I start pushing you quickly. What happens to your body? What happens to your body if that were to occur? Yeah, you get pushed back into your seat. You are feeling what we call acceleration. Now, imagine if you were driving Lightning McQueen. How cool would that be? Yeah. Now, Lightning McQueen here is an example of a race car, like the one I was showing you yesterday. Zoom, 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 zoom. Woohoo! Now, I've never been in a race car. I've never even been in a really fast car. Many of you know that I still drive a 1997 Jeep Grand Cherokee with 250,000 miles on it. And the only thing that works on it is the engine, thankfully, so far. And so when I try to accelerate, I really don't feel the acceleration much in my vehicle. But maybe your vehicle is a little bit newer and has a little oomph to it. And maybe when you're at a stop sign or stoplight and whoever's driving presses on that gas pedal, by the way, do you know what the gas pedal on a car is also called? The accelerator. Yeah, the gas pedal is also called the accelerator. So when your foot goes on the accelerator, guess what happens to you in the car? You accelerate. You go faster, right? You go faster. That's what acceleration is, isn't it? Well, if we were to compare two vehicles, Lightning McQueen and Mater, I'd be like the Mater in my Jeep, and somebody else would be in like a regular, more updated car. And they were to have a race. Let's say we go over to the Island Speedway where you can race legally, not on a public highway or a public road. But let's say these two vehicles go over to the Speedway, the drag racing track, and have a race with one another. Who do you think it's going to be that will be left in the dust? Probably Mater will be left in the dust, right? He'll be way in the back there because race cars are built for speed. They are able to change their speed down a track, which would be a measure of its velocity, speed in a given direction. Race cars are able to change their velocity a lot faster than other vehicles. I think we get that, right? So we can define or describe acceleration as the rate of change in velocity. The rate of change in velocity. I want you to be thinking about what these words mean. Rate, change, velocity. We'll get to that in a minute. But first, I want to explain to you why Lightning McQueen was in such a rush and left his best friend Mater in the dust? It's because he was going to see somebody. What's her name? Sally? Yeah, I think Lightning McQueen had a little date here with Sally, and poor Mater was the third wheel, so to speak, in the dust there. But thankfully, they both are obeying the sign here, which says stop, which has made their velocity equal to 0 right now, giving their friend Mater some time to catch up to them. But let's go back to that definition or description of acceleration. Acceleration, again, is the rate of change in velocity. Well, let's break apart these words here a little bit. And if you were paying attention yesterday, I think you know where we're going with this collection of words here. Again, acceleration. Here we have acceleration. It's a word we're going to be looking for. Call it out if you know what the word is means mathematically. You got it. Equals to. So let's take this definition and start creating a mathematical equation or a formula with it. So capital A stands for acceleration. The word is, we can substitute in the equals sign. So acceleration is equal to something. Well, what is it equal to? Well, we said the change in velocity. Change in velocity. Call it out if you know what the word change means mathematically. Good. Subtraction or the difference. If you were a cashier in a store and I gave you a $10 bill for something that only cost $5, I would expect some change. And how would you calculate the change I would be entitled to? Hopefully, you would take $10 and subtract the $5, and you would give me the change of $5. The difference between two things, the change in something implies subtraction. So here's how we might write that out. Acceleration, acceleration is equal to, acceleration is the difference, subtraction, between two velocities. And we're going to call it the final velocity minus the original velocity. So the original velocity is subtracted from the final velocity. But there is one more word we have to account for here in this definition, and that is the rate of. Call it out if you remember from yesterday what we said, what the rate of something means in a science equation. Think about the pulse rate. It's when something is compared to time or divided by time. So from these words in the definition, we can arrive at or create this mathematical equation which will allow us, enable us to calculate acceleration. So acceleration is equal to the final velocity minus the original velocity divided by time. That's what acceleration is. Now, I know that might seem like a mouthful to you right now, and it certainly is a lot of words to write down. So in science, as in math, we like to use symbols and abbreviate things to make it easier for you. So let's see how we can write this equation. We use letters. Capital letter A is for acceleration, and that is equal to capital V, and we call that those little letters there a sub. Just like a submarine is below the surface, a subscript is below the surface of the regular letter. So V sub F is the final velocity, minus V sub O is the original velocity. And we put it in parentheses there because it's all of that together divided by time. So here is our formula or our equation for acceleration. Acceleration is equal to the final velocity minus the original velocity divided by time. Everybody cool with that? So that is what acceleration is. And when you do the math and you come up with an answer, a positive integer, that would be a description of the acceleration of a vehicle and how much that vehicle is going faster because its final velocity is bigger than the original velocity. So this equation for acceleration will result in a positive integer. But I've been accenting the syllable, the first syllable in this word, acceleration, because there's another kind of celeration. And I'm not talking about celery on a salad. What I'm talking about is deceleration. Deceleration, scientifically and mathematically, could be described as negative acceleration. In other words, using this same equation, acceleration equals final velocity minus original velocity divided by time. If your answer comes out to be a negative, that means a couple things. It means that what you are determining the acceleration of is slowing down. Look at the equation here. The only way to get a negative number is if the original velocity is bigger than your final velocity. So if we're in a sports car and we're starting off fast, if your original velocity is halfway through the race, and your final velocity is at the end of the race when you have stopped, or if the velocity of your vehicle at a stop sign or a stoplight is 0 because you have stopped, that means your final velocity is smaller than your original velocity. So if you take a big number and subtract it from 0, what kind of integer are you going to get? A positive or negative integer? Hopefully you're going to say negative. And a negative number divided by some amount of time is going to result in a negative answer. So if your answer for that equation comes out negative, then you are describing a negative acceleration or deceleration. Something is starting to go slower. So if I give you a word problem, if you do the math correctly and you come up with an answer, you should know just by the type of integer your answer is, a positive or a negative, you should know just by looking at that sign whether this object is going faster or going slower, accelerating or decelerating. So I'm going to give you a moment right now to do this example problem in a space in your book. Find an open space And if you need more space, you can turn to the very back of the book. I have a blank page back there that you can use. But I'd like you to use the 5 steps of solving word problems to see if you can solve this and see if it is accelerating or decelerating. So take a few moments to do this now, and we'll talk about it in a moment. All right, we're back now with the last word of the day, and that word is momentum. 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 Now, let's look at this little picture here of a mouse. Now, a mouse might frighten you. And if a mouse anybody afraid of mice? Raise your hand if you're afraid of mice. Okay. If you're afraid of mice, the sight of a mouse might cause you to move away very quickly. You would be increasing your momentum if that was the case, taking the mass of your body and moving it at a certain velocity away from the mouse. You'd be increasing your momentum. How about an elephant? Are elephants afraid of mice? I think they are. I think, I don't know if it's true or not, but if this elephant saw the mouse, the elephant might run away, right? The elephant would be increasing its momentum as well. But now I want you to think about the relative masses of a mouse compared to an elephant. And I'm going to put you into this picture here and ask you a question. If this were you, if this stick figure was you, and let's assume you're not afraid of a mouse and you're not afraid of the elephant, and I were to ask you to move these two animals, which one do you think would be easier to move? A little mouse or a big elephant? And all we're comparing is really not the type of animal, because I got to be honest with you. If this were really an elephant, I would not want to be standing where this stick figure was right now. Believe me, I would not want to be standing there. By the way, have any of you ever seen Lucy, the Margate elephant at Margate, New Jersey? Raise your hand if you've ever been there. It's actually an elephant that you can go inside of. It's really cool. Google it later and you'll see what I mean. Anyway, what I really want you to compare here is not the animal, but their relative masses. Little mass, big mass. And my question is, which one would be easier for you to push, to move? A small mass or a big mass? Call it out. Call it out. What do you think? Hopefully you're taking the obvious answer that it's easier to move a lower mass. Well, momentum describes how difficult it is to start or to stop an object. Let's say you have a mouse charging toward you and you have an elephant charging toward you. Which one do you think would be more difficult to stop charging toward you? The mouse that you could probably step on, and we're not promoting injury to animals, or the mouse, or rather the elephant that could step on you. Which one do you think it would be better to run away from? Run away from the mouse or run away from the elephant? I'd be running away from the elephant, because that elephant could do a lot more damage to me, because it would be a lot more difficult to stop the elephant than it would be to stop a mouse. What we're describing is momentum, the difficulty it is to start or to stop an object. Here's another example. Let's say there's two vehicles, a tractor trailer and a motorcycle. Now, I've never ridden a tractor trailer. I've been in one, but I've never actually driven it. But I have driven motorcycle compared to my big old Jeep. All right. And I can tell you from experience that if this were my big old Jeep And this were my motorcycle I used to have. Yes, I used to ride a motorcycle every day here. Used to have a 750 Honda Nighthawk. It was a beautiful red motorcycle. Some days I miss my motorcycle. But I can tell you from experience that it was a lot easier to start and stop my motorcycle than it was to start and stop my big old Jeep. And if we were really comparing it to a big tractor trailer here, big tractor trailer is even more difficult to start or stop. So think about this for a moment. Let's say a deer runs out in front of the tractor trailer in this particular example. We've got a deer running out in front of a tractor trailer, and behind the tractor trailer, we've got a motorcycle. Okay. Do you think the tractor trailer is going to slow down at all when the deer runs out in front of it? My guess is probably not. And that deer is going to end up as a hood ornament for the tractor trailer. And the motorcycle driver probably won't even realize that the truck ran over a deer, because that truck is just going to keep on going. In fact, a truck would be very foolish to try and slam on its brakes for a little old deer on the highway. Sorry, deer. Why? Because that truck has so much momentum, it would be so difficult for that truck to stop that it would probably jackknife and cause many more accidents and deaths, human deaths, than it would to just run over the deer. However, what if the situation were reversed? Think about this. Let's say the motorcycle driver is riding along a road and you see a deer running out in front of you. Should the motorcycle not do anything and just run into the deer? I don't think so. I know a number of people who have had very bad accidents by being on a motorcycle and running into a deer. In fact, one year I almost ran into a deer. Thankfully, I didn't, because I know if I did, there wouldn't be much left of me, because I would have so much momentum in that little motorcycle and no protection that the deer would have caused a lot of damage to me. I would have been the hood ornament or the rack ornament for the antlers of that deer. It was a big buck, believe me. However, the automatic response of a motorcycle driver might be to tap on its brakes, because a motorcycle can stop very quickly. And if there was no tractor trailer behind the motorcycle, motorcyclists might even be able to stop, or at the very least, maneuver or swerve out of the way to avoid hitting the deer, assuming there's no other traffic in any other lanes. However, if you're a motorcyclist and you stop short, which you can do on a motorcycle, and you've got a tractor trailer behind you, that tractor trailer is not going to have a deer as a hood ornament. It's going to have you as a hood ornament, because a tractor trailer has a lot more momentum. It's a lot more difficult to stop than it is for you on an itty bitty little motorcycle. So how does this all relate to science? Well, let's come up with an equation for momentum. Momentum relates to both mass and velocity. In fact, if we use this equation, the equation for momentum, capital M, is equal to the mass of an object, lowercase m, multiplied by the velocity of an object, lowercase v. So uppercase M stands for momentum, lowercase m stands for mass, lowercase v stands for velocity. Now I'm going to give you a little bit of time here for you to work out a word problem of the momentum of a truck. So if a truck has a mass of 10,000 kilograms and is moving at a velocity down the highway of 100 kilometers per hour, what is its momentum? Take a few moments, use the 5 steps of solving a word problem, and see if you can solve this momentum problem. And we'll take a few minutes together as a class to discuss the problem together. Once you've got that problem solved, I'll say bye-bye for now, and tomorrow will be a lab activity that we'll be doing together. So bye-bye.